그럴 수 있어 정말? 너무한 거 아니야? It's too much, isn't it? How could it let you be? Okay, IL is mainly vibrational mode. Emission spectroscopy is fluorescence. Fluorescence. And IR is absorption. And electronics transition is for the absorption or emission. This is related to the color, to be visible. Nucleus beam is what we will do today. And okay, in IR, what's per centimeter? Another terms, wave number. It is a frequency unit, and if it's higher, then high energy. This is a high means wavelength is short. 하고 답을 한번 까볼까? 누가 해줬는지? (3000) is fixed. These are CH vibration. This is arcane evidence. Double bond NH. CH double bond a little higher, so peak shows up here. Triple bond and peak a little further coming up here. Okay. CN double bond, triple bond, this comes from 220, 2200. Less than 3000, higher than 3000. Okay, higher than 3000, below the peak here. That's all what we need. That's all what we learned. One more. Very strong peak here. So today we are going to study the last technique for this semester, NMAP. And today I invited two, Dongwon and Nansa. Okay, Dongwon first.
Hello, my name is Dongwon Kim, and what I'm going to introduce today is NMR spectroscopy. First, NMR stands for Nuclear magnetic resonance spectroscopy, and it means that NMR is one of our phenomenon that atomic nuclei in magnetic fields resonate with some electromagnetic wave in specific frequency. So, as in the picture, there's nuclei NMR in radio wave. So we in NMR is mostly use the range of 400 to 900 megahertz wavelengths, and it's a radio wave. So before to say about magnetic field, I bring this TMS for the reference materials in NMR. It's called tetramethylsilane, and usually we use these materials for the reference because, as we can see, there's 4 metal and all the hydrogen have a same chemical environment, so it only get one peak. So it is good for the reference, and other characteristic is that these materials does not react well with other materials, so it is good for the reference. So if there's no magnetic field, like last picture, the nuclear magnetics are very random and there's no direction. But like right picture, when we apply some magnetic field, the nuclear magnetic arrange with the same direction of magnetic field, or some of nuclear is arranged with opposite direction with magnetic field. But not all the atoms arranged like that. Some are not arranged with the same or opposite direction of magnetic field. That is, you can see the carbon or oxygen or sulfur is not non-magnetic nuclei. This is because if the atoms, protons and neutrons are even numbers, then they don't have some magnetic characteristic, so we can. The NMR is giving the magnetic field and check the spin, but like this carbon, oxygen and sulfur, we can check with the NMR. So most commonly used nuclei is hydrogen and 13 carbon, and other can be checked also. So this is the very simple picture of process of checking NMR. So there's no magnetic field, and second, we apply some magnetic field, and the nuclear will arrange the same direction or opposite direction. Then when we give some electro wave, that I said radio wave, then in specific frequency, they will be changed the spin direction, and when they change the spin direction, they have some energy, and NMR check which frequency and the energy, and they process some data and make a graph like bottom of picture. Thank you.
in this diagram, there is an x-axis. It is a chemical shift. Chemical shift is the differences in shielding compared to TMS. Then what is the shielding effect? Around the atomic nucleus, there is electrons. Electrons also affect magnetic field, and it affects opposite sides of just external magnetic field. So nucleus feel less magnetic field by electrons. In this example on the right side, there is halogen molecules attract electrons because they have large electronegativity. As a result, around the hydrogen atom, they have less electrons. Chemical shift become larger as electronegativity is larger. Chemical shift change by surrounding of atom. Chemical shift of TMS is 0 because it is a standard and its relative value between TMS. Its unit is ppm, hertz per megahertz. Megahertz is external magnetic field. It is a resonant frequency per magnetic field. And 1H NMR is detecting hydrogen. In this picture, HN and HB have a different chemical shift because they have different surroundings because there are another O in between the HN and HA and HB. If do 1H NMR, you usually make solution. At that time, solvent should be magnetically isotropic. The fewer elements you want to analyze is better. Also, do not react with solute. While I researched this part, why solvent use deuterium instead of hydrogen, like that for solvent. In 1H NMO, solute is very small parts than solvent. If solvent has hydrogen, it is hard to detect. But another question, not only 1H NMR, but also detecting 13C NMR use also deuterium. The reason is what is the locking. Locking is the process of stabilizing magnetic field. Fluctuation of magnetic field like this can affect to the resolution of NMR. So we need to stabilize magnetic field like right side of the picture. NMR uses absorption wavelength of deuterium to check locking progress. Related to the locking, there is a shielding. It provides a uniform magnetic field across the entire sample. Around the sample, there is some coils and it measures magnetic field. In this picture, there is a locking signal. It is related to uniformity of magnetic field. We need to do experiment where the plates have a highest lock signal. Lastly, 2D NMR. 2D NMR used in the big molecule or organic molecule it is hard to measure in 1D NMR. 2D NMR experiment to pulses can be used to obtain a spectrum in the form of a two-dimensional map of the correlation between atomic nuclei. For example, COSY, DOSY, and HNBC and HSQC. The right side of the sample is the COSY. Thank you.
수고드렸어. 관심 많으시니까 밥 쪼개가지고 나눠가지고. 네. 관심 많습니다. Okay, based on the presentation by Dongwon and Hyun-Seok, let's continue. NMR. Okay, NMR, nuclear magnetic resonance. Nuclear magnetic resonance. What's that? Nuclear magnetic resonance. NMR is, what did I say? Another nickname of NMR? No more reaction, no more research. So powerful. Why is it so powerful? Let's look. In quantum mechanics, when we basically this is electrons movement. Not in the box. Box is just a imaginary model, particle box. The real situation is only force applied to this at a small scale level. Only force is the electric force, electromagnetic force. Then there is a positive charged nucleus, and electron is traveling. Once it sees nucleus near enough, then they start to interact. They open your eyes. When the electron pass by, if it feels electric force, and it comes near to the nucleus. Now they start to reside together in a given space. Okay, that's what happens. And if there's only electric force, they will collide. But there is repulsion at the first two. So once the electron has the kinetic energy. If the electron has the speed, then they have the kinetic energy. They start to rotate. And then Rutherford model was a little strange model because once they move around, then they need to lose energy. But in quantum mechanics, in the beginning we assumed they keep one status, and then another state. It can jump, but it doesn't change those continuously. So in the model, after the old quantum number that we found, seems like there's another splitting. Everything should be the principal quantum number and orbital quantum number, and angular the orbital quantum number is given. See, there's a two splitting was found, and that scientist name, that effect, there was a splitting. Anybody knows? There should be singular state, but there is another state. It seems like there is another splitting happens. Somebody's effect, Helmholtz effect, Daniel effect. Whose effect is it? Definitely you have heard the name. Daniel? Anybody? 야, 들어보지 않았어? 써지는 거 생각이 날 듯? Zeeman effect. Sounds like a German name. Is it German or English?
German.
Sounds like a German. So Zeeman effect. So there seems like there's another splitting was observed. There is another quantum number. So what is the first quantum number? Hmm?
자기.
That's the third one, force. In the magnetic field, that's a spin. That's the electron spin. So before that, we didn't think about this spin effect. Electron seems like it has a spin effect. One effect is the circular motion like this. This is orbiting, 공전. Spin is self-rotating, 자전. So we don't know whether this electron is really spin or not. Nobody has seen it. But seems like we see the effect of spinning. So now somebody was suggested that to one graduate student suggested to his advisor, Judy Wilson, and Judy Wilson said that that's bullshit. It doesn't make any sense. Go away. And he gave up to publish it, and some years later it was published. And that guy got Nobel Prize. So don't believe you are Judy Wilson. You may lose your chance of getting Nobel Prize. This concept seems like at least effectively it's showing up everywhere. Electrons never stop. Electrons seems like they are always spinning, either this way or this way. This way or the other way. Two states they exist. And much longer time later, it was found that not only the electron, nucleus is also spinning. Proton is the simplest nucleus composed of only one proton, and that also has a spinning effect. If they spin, the effect charged molecule move, then that induces magnetic field. There is a term that magnetic force is relativity effect of moving charges. 자기력은 전기력의 상대론적인 현상이다. If the charged particle moves, then that induces magnetic field. If magnetic field is changing, there is charge change happens, inductive current happens, and they cannot be separated. We have a separate magnet, we have charges, but if you think in a relativity the way, and they are not separable, they are basically same event. It happens always together. 자, 찾아보고 수업 시간에 그거 다룰 수 없으니까 you study about that. Anyway, if charged particle rotate, it induces magnetic field, and it has only two states, half this way, half this way. Then this is effectively behaves like one magnetic bar. NS. If there are no external magnetic field, we cannot distinguish them. That's why it looks like one energy state. If we apply magnetic field from outside, that's what heated. Then those singlet becomes two doublet, two different energy states. That's what we found. And that's proportional to the magnetic field size applied from outside. If a magnetic field is becoming bigger and bigger, and that energy state is also getting bigger and bigger. So these spinning particles, they are in two states. Usually they are in random rotation, and we don't see that. Once outside external magnetic field is applied, then they align, either following the same way or the opposite way. And then two has slightly different energy state. Electron, proton, which one moves faster? If electron moves faster, then this energy, the split difference, which one may be higher? Electron is much higher. So that electron energy, the difference is much higher. Nucleus is moving much slower, and that effect is also very, very small. Okay. Very small, that's why the one said it's a very later stage of radio wave range. Very small energy gap could be observed for nucleus of the spin. Anyway, that was the starting point of the studying of this amount. And proton seems like it has that effect. Proton, along with the carbon, that's most important, the atom in organic molecules. Most of our organic molecules, as we have seen here, CH vibration, organic molecule should have a carbon and also proton. If you can see those proton and its status, it's a very good information to understand the organic molecules. And what can we see here? So for the proton, now proton has, if there is a proton in organic molecule, it is connected to either to carbon or it is connected to oxygen, then it's alcohol, or it's connected to oxygen attached to carbon. It has a little different environment. So biggest environment, we can see, first of all, those effects, the proton NMR, it has from 0 to 10 range usually we see. Okay. Unit is a ppm. What is a ppm? Second? Part per billion. Okay? It's like a percent. So that means that there is a reference value here. Okay? Reference value may be in the middle. And hence said by giving irradiation, radio wave, and then they jump up to this, and that energy value is here. And this energy gap is very small. And among them, we need to distinguish those 1 out of a million. That's very, very, very small. That's why the energy status, depending on magnetic field status, is shifting a lot. So the NMR machine, strong magnetic field is there. If you pass by with a metal, then it can interfere with the magnetic field. Then this can be shifting a lot. Then this 1 ppm it moves like 100 ppm like this. So the signal is shifting so much. That's why we need to have a locking. So I'm the fighter, the operator, and then I'm following the enemies of the fighter plane. And they're moving very fast. It's very difficult to shoot my missile. Then what do we do? And following those signals, and then those signals lock on the target. That means once we lock it, then our detector is moving together with the fighter target. That's locking. Okay. To do that, we use the deuterium solvent. That's another magnetic the NMR effect it has. So using that desolvent, we lock to the target. Then even though there is interference of the change of external magnetic field, those four signals are following that signal. Maybe in the middle of here. So using this technique, now we distinguish those 1 ppm unit each, so totally 10 ppm. Carbon 13 is also magnetic, the NMR active. So carbon and NMR, if you look at them, then that's a very good information we can use. And carbon 13, the stable, most of them are stable, but standard is carbon 12. Existing amount of carbon 13 is about 1% of carbon 12. So that's why signal is at best it can be 1% of original carbon. That's why carbon usually NMR is quite clean. Carbon is very rough usually because the signal is so low. The naturally occurring carbon 13 amount is only 1% of the total amount. So to get the proton NMR, you need to have several milligram. 10 milligram is usually good enough. So if with a high resolution NMR, maybe 2-3 milligram is fine. But carbon, most likely you need to have more than 10 milligram or 20 milligram, high amount. If not, your signal is low. Now NMR, proton NMR, about the 10. Carbon NMR is about the 0 to 200 range. That's partially because proton is moving very fast. That's why if you use 300 megahertz NMR, then the signal is from them separating is quite big. Carbon is moving much slower than proton. That's why even you use 300 magnetic, the same machine, the splitting is only quarter, 1/4 of the proton because of the slow moving. That's why seems like it's the same unit we use, but that standard is only 25% of the proton. That's why those relative amount seems like bigger, even though it's the same range, but if it's 4 times bigger, then it looks like it's number is big, but it's not really big. Okay. So proton 0 to 10, carbon 0 to about 200. That's what we see. And those difference of this we call chemical shift that reflects the environment of that proton. Now those environment is whether this proton has a lot of electron around or not. If there's a lot of electrons, those electrons never stop, they are moving. If external magnetic field is applied, and this moving electrons, it generates induced magnetic field. If external magnetic field applied, then this induced magnetic field will resist against the external magnetic field. So that means opposite direction of a magnetic field is formed nearby, and external magnetic field effect is slightly decreased. Then those energy gap becomes a little smaller. That's what is shown here, this direction. TMS was shown in the previous presentation. Silicon in the middle. Silicon is electropositive. That means it does not attract electrons, giving out the electrons to the carbons. That means the carbon CH3 has most rich electron environment. That's why we use silicon compound as a standard to make it push to this direction. If there's any electron withdrawing group, then they attract the electron from carbon, then they are relatively has lower electron density. Okay. Then the resisting effect is smaller, that's why it moves to this direction. So we call this direction is shielded, protected by electron. This is the de-shielded directions. So altogether, electron-rich environment, electron-poor environment. That's what you can see from chemical sheet. Okay, electron-rich, more electron withdrawing group, then it moves to this direction. Same for the power. Okay, that's a general the view we see. Here we have proton source here and proton source here. Now this is attached to oxygen. So oxygen attached to one is a little further downfield. So we call this a downfield, this is a upfield. Shielded, de-shielded. Okay. So this one is showing up a little up the downfield here. This one is less shielded, so it shows well here, a little upfield. So we can see those are two different the environment of the two protons. That's one information, chemical sheet. Now for the machine, so we need to have magnetic field and put those samples inside here. And hence I said shimming to make this signal symmetry. That's one way. To another trick is to make this sample symmetry, it rotate. And this tube rotate to make average out those shape difference. And then give the energy to jump this two energy state of the proton, lower and lower state, get this energy and get excited to upper state here. And then slowly it is relaxed to come back. And then we measure those signal, those difference signal. If it's a de-shielded, shielded, then becomes smaller. De-shielded becomes bigger. We measure those difference of those. Now, to record this, now can you think NMR is absorption spectrum or emission spectrum? IR was absorption. We didn't learn fluorescence here. Fluorescence is emission, observed and we emit. NMR, does it sound like absorption or emission? That's emission spectrum. Because to excite that, you give chunk of the different wavelengths of radio wave altogether. And some of them is excited. And then how much excited, we can measure by their emission, whether it comes small range or the bigger range. The NMR is kind of the emission spectrum. Okay. So using this, now we can think that if those two protons are in the same environment, we can see one signal. If they are in two different environments, we can see two different peaks. Now we have studied this kind of a shell conformation change, conformation of flip over. Now one is axial, one is equatorial, and in principle they are different, but in room temperature it moves very quickly. It's a conformation argument. That's why at room temperature we see only one peak. It's averaged out peak. But if you lower down the temperature, very, very low, minus 90 degrees, now they start to separate into two peaks. And one and the other has a different energies. Same thing for the rotation, we have seen conformation of the isomers. They also can be separable by lowering down the temperature. Now I explain. So this is downfield, this is upfield, shielded, this is de-shielded. Okay? And TMS is used as arbitrary chosen reference because it's quite shielded. So by putting TMS together in the sample, not only locking, okay, by putting internal reference, and then this single peak we use as a 0 ppm. is arbitrarily chosen, randomly chosen. So then you should say, I use the TMS as reference and use that as a JLPT. Okay. Now we put our sample here and we see. If it is simple, I can just directly connect it to the carbon. They are usually around the 1 range. It's relatively shielded. No electronegative atoms. If there is any heteroatom, oxygen, carbon, halogen, it comes around the 3 plus. Now, this aromatic ring usually comes from 7 range. There's some explanation that aromatic ring has aromaticity, there is ring current. If ring current happens like this ring current generates magnetic field. This is ring, then magnetic field is generated like this. So this ring current make very strong local magnetic field, and that's the explanation of aromatic ring has quite low stage here, but that's about the 7. Double bond has the half effect like that, so this is the 5 or 6. And carbonyl, next to carbonyl or allylic or benzylic position is about 2. So this is the general, the chemical shift. Let's summarize again. Alkane around 1. Halogen N or O around 3. Aromatic around 7. Alkene is in between, just a little appealed than aromatic. And carbonyls alpha position is around 2. Or allylic, benzylic, those are around 2. So TMS we use reference, and then alkane around 1. And carbonyls alpha position around 2. Any heteroatoms, they come also. Carbonyls alpha position and also benzylic position, those around 2. And also allylic is also around 2. Any halogen or oxygen heteroatom around 3. And aromatic ring around 7. Okay, that's approximate number that we can see. Specific examples. This is good now. And then I cover specific now. Okay, with this molecule. These hydrogens attached only to the carbon. This carbon is connected to the carbon. So those are like alkane. Okay. Then these carbons, 9 of them shows up around 1. And if you measure those area of this tip, 현모야 돌아와라. 고개만 끄덕거리지 말고 돌아와. 형! 잘 들어. So if you integrate this area, that is proportional to the number of proton. Here is a 9 proton. So this is integration of those areas. This is 9. And this one is about 3. So 3 to 9 is a 1 to 3 ratio. By looking at those peak size here, integration of this, then we can count relative number of protons. This one is connected to the oxygen. Oxygen 3.2. Okay. Alkane 1. Carbonyl alpha position 2. Heteroatom 3. Aromatic 7. So here 9 to 3. 9 to 3. There is no reference for which one is the 1, so you should calculate relative amount. Okay, it's 1 to 3 ratio of those protons. Okay, this molecule, how many proton signal do you expect? Identical one, it will show you 70. Question is how many different protons are here? 3. 2. This one and this one is identical. This proton and this proton are identical. This one is also identical because it's symmetric. You may see only 2 peaks. Where this peak is a benzylic position. Benzylic, allylic, carbonyl, sulfur position around the 2. Okay, around the 2. This is aromatic, around the 7. Okay. If you look at this molecule through carbon NMR, how many carbon can you see? Even though we didn't look at the carbon NMR yet, but how many different carbons are here? It's a 3. 1, 2, 3. Geodesic symmetry. Okay? Even though we do not know the real or the spectra, at least we can say how many different peaks we can expect. Okay? Okay, this molecule. Methyl bromide. Now we see a little more information. Chemical shift, let's check first. There are 2 kinds of proton. One is like alkane, it's connected to carbon. That should come around 1. Around 1. That's a 3 proton. And then here, CH2. Attached to this, we don't count. We see this heteroatom around the 3. Relative amount 2 to 3. If you divide 1.5 to 1. Chemical shift position and relative ratio 2 to 3 makes sense. Now you see some kind of a splitting incident. That is a second important information from proton NMR. One information is chemical shift. How much electrons are around? That's the information. Okay. Now second information. Now if this is connected to this, each protons are like a spinning magnet. Right? If there is next to this carbon, there is a nearby another protons. It is like spinning magnetism nearby. Because of this magnet is either up or down. So if you have a 1 hydrogen next to you, then your signal becomes split double. If there is a 2, you split one more time, make it 3, 1 to 1 ratio. If it is 3, it is split into 4. Makes sense, right? So then this one has neighboring one. If it is the same to each other, they don't interact with each other. It's just showing only one peak. But if there is this peak, 3 proton nearby, then this peak becomes split 3 times and then make 4 peaks. This one, there is a neighboring 2 protons, split into 3. That is the information we can get. And if you look at these values, they interact to each other. Even though this generates, because of these 2 generate the 3 peaks, this generates 4 peaks because of this 3, those interactions are equivalent to each other. That's why this relative, the interval, so-called coupling constant. So this is the coupling we call. Coupling constant, this one and this one is the same. That means this coupling constant is sometimes big, sometimes small. If you can match the same coupling constant one, you can connect which one is a coupling with which. The last page also showed the COSY 2D NMR, which we are not going to cover here, but 2D NMR, you get 1 proton NMR this direction, same one here, and this is the diagonal direction, so it is the same pixel coming out. And by finding out those coupling constants, okay, this one and this one looks like this coupling constant is the same, that means these 2 are connected to each other. This kind of information you can obtain from 2D NMR. So coupling constant can tell you which one is reaching the coupling, and this size tells you exactly the partner of those couplings. So those coupling, if you look here, isopropyl bromide. This is CH3, CH3, they are identical. And this is connected to carbon, they should come around 1. partner is only this, one proton. That's why this peak shows double. Now for this, it has a 3 here, 3 here, totally 6. If it is 6, then splitting pattern should be 7. And it shows 7 peaks like this, including this. Relative ratio, this is 1, this is 6, 1 to 6. 1 to 6. And this is connected to heteroatom, 3 point something. Oh, it's a little higher, but that range. Okay. So two informations, chemical shift and coupling constant. Then we can guess those chemical structures. So splitting pattern, if there is no neighboring the protons, it's a singlet, just a single peak. If there is a 1 proton next to carbon, then doublet. 2 proton, triplet. 3 proton, then quintet. It's a 4 proton means 4 protons, 2 here, 2 here. And that's a 4 proton. Then you can get quintet, 5. Is there any option that you can have equivalent of 5? 3 here, 2 here, that's not equivalent to 5. Okay. If you have 1 here, 1 here, if they are not identical, then you will get double over double. Let me say it again. Here we are talking about same proton nearby. This proton if this one and this one is not identical, if it's XX, it's the same, then 1, 1 you have, then this one will show you triplet. But if this is this one, X, this is Y, if they are not identical, then coupling constant between this and between this is not same. That means bigger one we can divide first, and small one we can divide again. The peak shape originally it was the same, it was a triplet, like this. If it's not same, then it's like this. This coupling constant and this coupling constant is not identical. This one we call doublet or doublet. This one is a triplet. It's a different. Okay? Now, 2 and 2, if both sides are the same, it's a possible. But 2 and 3 equivalent, is that possible? You cannot think of any option like that. So that's why it didn't show the 5 equivalent protons. Only option is we have the 6 equivalent one here and here. So then we can get 7 peaks, so for the sector. Okay. This pattern is what you can expect. And those are divided and divided further. That's why 1 to 1, 1, 2, 1, 1, 3, 3, 1, kind of the separation like this. Those effects we can expect. That's coupling constant. So that's another information you can get. Now, if those environment is equivalent, 3 carbon, this 3 proton is equivalent, and these are equivalent to 2, then it shows only 1 peak, single peak. They don't couple, it just only shows 1 single peak. Now, those coupling constant happens, usually, it's connected carbon positions. If it's go further, 1 more, then usually it's very big, and usually we don't see. Coupling constant in your level, just think about directly connected 1 to position, then it can couple. Okay? 1 to position couple, 1 3 position, very rarely. In your level, you just ignore. Okay, now let's look at this molecule. Before we look at this spectra, let's just think. This one, singlet, there is no coupling the nearby protons, and position of this oxygen is here, around the 3. Not around the 3, around 3 point something. And here, this one. Now, this CH3 is connected to this. This is almost alkane, around 1. Coupling, how many? How many coupling pattern? Doublet, triplet, quartet. This 3 has a neighboring of 2. Then triplet. And this comes around to 1 and triplet. Okay? Now this one, this CH2, chemical shift wise, alpha position of carbonate. Then around to 2. And splitting quartet because it has neighboring 3. Around to 2 and quartet. That's what you see. This is the first time you see this spectrum, that's why it doesn't come to your mind right away, but altogether if you look at triplet quartet nearby like this, then you can think, oh, it may be active group. Okay? Triplet quartet. This triplet, this one CH3, has no chance to be attached to heteroatom. It's only connected to carbon. That's why this triplet usually comes around 1. And this one has a chance to be attached to other heteroatoms. That's why usually this quartet comes a little downfield. And if you look at this pattern together, there may be acid group. Okay? And after these two done here, this one done, and then here, aromatic compounds. Now, in this aromatic compound, how many different proton there? Only 1? Or 2? Or 3? Or 4? How many different? 3? How can you count the 3? We have a 1, 2, 3, 4 proton, right? So which one is identical to each other? These two is identical. This is identical, right? Two different kinds. If they are different, then this is a 1, 2 position, they couple. Means this peak, it shows 2 peaks, and each of them, they interact with each other, it generates a double. Double of double. Here double and here is double. Then coupling constant here and here, they should be identical. Okay? And can you distinguish between these two? Maybe, in this case, this electron withdrawing group, this is a withdraw further, then this electron may be more dissuaded. So this peak may be in downfield. This is an electron donating electron side, then this may be a little upward field. So that much you can do next semester. For now, these two peaks can be different, and you generate the doublet, that's enough. Okay? Now let's look at this. Molecular formula is given. Now you have this. Can you guess molecular structure? 그래봐. 나와서.
네.
나와서 그래봐. 뭐라고 하는 말래?
나이트의 기억도.
So what's the molecule? What's the molecule? Tell me.
Like CH3, CH2, oxygen, CH2, CH3.
What do you call the compound name?
Ether.
What ether? It's a diethyl ether. The ethyl group here, ethyl group here, the oxygen in between. So these two is symmetric, that's why this is typical ethyl group of the form. And if you review them, so this group, this CH2 is attached to oxygen, that's why it shows around the 3. CH3 comes up around the 1. Okay? So this may be simplest molecule you can think. Okay? Now, if you look at here, if this proton and this proton, the green one and blue one, they are not identical. They are different positions. They are not related. Among these greens, this is identical, symmetry. Blues, they are identical, but green and the blue, they are not identical. If you change one each, okay, with the different things, they form totally different isomer, different connection, different structural isomer or different constitutional isomer. It's the same meaning, constitutional, structural. If those two protons are non-identical, they are showing different peak in NMR, and also if you exchange that, they form constitutional isomer. If they are identical, here, these three and these three, they are identical. Okay? Then in NMR, they show only one peak, no coupling. Those kind of protons we call homotopic. Homo means the same. Homotopic. So if you change any of them, it forms just the same molecule because they are identical. It's homotopic. So homotopic one, if you change it, it's the same product you can get. NMR shows only one on the peak for all of them. Now this we learned as prochiral. If you change one of them, then it forms here or here. Now it forms chirality center. And this kind of the position we call enantiotopic because it forms the enantiomer. If you change different position each, it forms the enantiomer. Enantiotopic, still NMR gives you same signal. It doesn't separate. Enantiotopic gives you same proton, they don't couple. Still, you get only single peak for each. If this is connected to chirality center, now, molecule here, if you change that, this is already an enantiomer, depending on the position on here. Now, if you change any of them, now you generate a diastereomer. Then, this kind of the position for diastereotopic. Diastereotopic one, you get two different NMRs peak because these two protons, depending on this environment, this is chirality center. Environment of the electron for this and for this is not identical. Okay, so I have Boyon here and then Yang here, so I have two protons. The protons effect coming from Yang and Boyon, it cannot be same. That's why diastereotopic, it behaves like different proton. You get two signal, you get even split between them, coupling. Okay? Chirality center is nearby. Spatially, this environment is not same. Even though it's connected to the same column, it's not same. Those are diastereotopic. Those behave differently in NMR. Okay? Electron environment is different and they behave differently. That's why in NMR, diastereotopic is very important. If you see same carbon connected two proton behave differently, that means nearby there is a chirality center. Okay? That's what we call diastereotopic topic. Now, by looking at this, can you tell whether this is a homotopic, enantiotopic, diastereotopic? Let's look at this one. What do you think? That's an enantiotopic. Because if you change that, this becomes chirality center. In NMR, how many peaks? Only one peak. Because this is showing not yet. Okay? Even though enantiomer is formed, enantiomer does not give you different NMR spectrum. Enantiomer is also physically same. Right? How about this? This is diastereotopic because chirality center here. Okay? That's why this position may be different. How about this? Homotopic, you think? If you change one of these and this, the product is same? Different.
Yes.
And that's a diastereomer or enantiomer? It's a diastereomer. Cis and transform is a diastereomer. So this is diastereomer. diastereotopic. Okay? You can think, environment of this is facing to this, it's facing to this. It's different. Right? In NMR, you see two peaks, two separate peaks. Okay? How about this? That's the diastereotopic because color is center here. How about this? That's also color is center here. Diastereotopic. This one. If you change one of this into T, still there is a plane, the symmetry on the plane here, right? Same molecule, homotopic. So I have to change it, but it forms enantiomer, diastereomer, and same molecule. Okay, that's what gives you the determining the fluid. Okay, this molecule. Now this molecule, if you look at this structure, this is on aromatic region around the 7. Benzenic position around the 2. Okay. This one is not directly connected. This carbon doesn't have any proton. That's why this is singlet. This one now, how many proton? How many different proton on this family? How many different kinds of proton on family? 3 kinds, right? 1, 2, 3. And this one coupled with this. This one coupled with this. That's why it looks like a little complicated pattern. But if you analyze them, this one will give you what pattern? Doublet, triplet, quartet. This one. It has 1 proton here, 1 proton here, 2 proton there, triplet. This one will give you a triplet, then you can find 1 triplet here. How about this one? This one has only 1 nearby. So this one should be doublet. So you have 2 doublet, same gig, and this one. This one is now 1 here, 1 here, double over double. Not quartet, not triplet. Those two can be same or can be different. That's why it's a little more complicated formula here. This much you don't need to worry about. I will give you only simple problem. Okay, this molecule. One of them. Let's start here. Okay, let's continue this. Okay, after here today, so we are going to continue. It's a proton NMR and carbon NMR the problem solving at the next time. And so let's decide the final exam date. Final exam, you have to look at the final exam schedule for. I'm thinking to take the exam again on the same time. The June 4, that's a Tuesday. Final exam June 4, the 11 a.m. in this room. 1 hour exam. The exam will be focused on the after midterm exam. Majority problem will come there, so it can may be easier for you to concentrate for that part. Alkene reaction, and alkyne, and alkene halide, and IL, mass, and NO. Okay. If you see any problem, then let me know as soon as possible. So on Thursday, I'm planning to buy you pizza one more time. So around lunchtime, you will get a pizza. So if you have any other schedule, 다른 약속 있으면 알 수 없지만 다른 약속 잡지 말라고. So around the noontime, you will have the pizza, and then we will finish the class. Okay, any question for this? Okay, on Thursday we are going to continue and finish those animals and structure